What if self-driving cars could hear in addition to seeing the environment around them? We introduce acoustic beamforming for automotive scene understanding by using passive traffic noise. Sound carries complementary information to light, and human drivers use the signal for scene perception and understanding. The presence of a fast-moving vehicle can be perceived just from the sound produced by it. For comparison, this is what you may see. In this scene, roadway traffic noise is caused by the vehicle's engine and tires, which add complementary information to the visual signal measured by cameras. In our work, we show how we can use acoustic signals for multimodal scene understanding. To this end, we introduce a large and diverse multimodal automotive dataset that's comprised of sound recordings from a 24x24 microphone array, long-range acoustic beamforming maps, images and point clouds from multiple cameras and lidars, and corresponding GPS IMU data. We investigate multimodal tasks, including object detection and frame interpolations using data from passive traffic noise, which leads us to favorable results in challenging automotive scenarios. Our application shows the potential of utilizing the complementary nature of sound to the photon-based sensory information. Sound travels as pressure waves and can be measured by a microphone. With additional microphones, recordings have directionality to them, for example, stereo sound. Extending this idea, within the array of microphones, one can virtually scan the ambient space for sound signals, simply by adjusting the time delay of measurements between various microphones. This process of scanning and directionally measuring the sound signals is called acoustic beamforming. In our work, we construct an array of 1024 microphones and mount it on a prototype vehicle to scan and measure ambient traffic noise via acoustic beamforming. Here, we visualize the measured beamforming signals that localizes the sound intensity by overlaying it on an RGB video. As can be seen, the sound source can be spatially tracked from microphone array measurements. Here, we visualize a scene with a vehicle and the corresponding beamforming signal as measured by the microphone array. As described earlier, a higher number of microphones result in a higher or a better resolution of beamforming signal and hence a higher accuracy in localizing the sound source. However, integrating and mounting an array of several hundreds of microphones on a vehicle can be challenging. We introduce neural aperture expansion method that helps us to achieve a virtually larger microphone array size from a smaller aperture signal. In addition to the microphone array to measure sound, we also equipped our prototype vehicle with 5 cameras, a lidar, and a GNSS system to capture multimodal information of complex automotive scenes. We captured a large beamforming dataset that covers diverse, commonly occurring traffic scenarios, including rush hour traffic, construction zones, and busy intersections. Here, we visualize some randomly selected sequences from our multimodal dataset, with the beamforming signals overlaid on camera data. Our dataset covers a wide range of common traffic classes such as vehicles, traffic signs, and pedestrians. We collected data with our prototype vehicle stationary as well as moving, which should address concerns about its engine noise. Our dataset also contains an almost equal number of day and night instances to enable exploring applications in diverse and challenging scenarios. We investigate multimodal scene understanding as follows. After sound signals are picked up by a planar microphone array, we perform long-range beamforming by scanning temporal delays. We then get a higher resolution beamform maps using neural aperture expansion. The acoustic and vision signals are then processed to extract the multimodal features that we then use in downstream tasks such as object detection or frame interpolation and extrapolation at ultra-high frame rates. For both tasks, we've observed that the results get consistently better when using RGB images in conjunction with beamformed maps and neural aperture expansion. Here, we show traditional object detection in a challenging nighttime traffic scenario, where detection completely fails due to low light and glare. However, the presence of the car can be detected via the complementary acoustic signals, and our multimodal approach results in robust object detection. Here are a few additional examples showing our method resolving ambiguity in scenarios where RGB cameras fail. Acoustic beamforming allows us to recover scene information that is otherwise impossible with vision-based sensors. For example, in this scene, the vehicle is occluded by the divider, but is revealed in the beamforming signals. Similarly, the car partially occluded by the pedestrian is completely revealed in the corresponding beamforming signals. We've investigated acoustic beamforming as a sensing modality for scene understanding, which can resolve ambiguity in cases where photon-based sensing fails. We've released the dataset, code, and other material which can be found on these QR codes. We are very excited to see how the researcher community builds upon our dataset and pushes the frontiers of using sound for scene understanding. Thank you.